Thank you for having me once again on the Circuit Forge network. Today, we're taking on a topic that has fascinated people for over a century. What makes airplanes stay in the sky? Have you ever sat by the window on a flight, looked out at those massive wings, and thought, how on earth is this giant machine, weighing hundreds of tons, floating thousands of feet in the air? Why doesn't it just fall like a rock? Well, today, we're going to break it down in a way anyone can understand. Let me start by asking you this. Have you ever put your hand out of a car window while driving? When you tilt your hand slightly, you feel it push up or down, right? That's actually one of the simplest demonstrations of how an airplane wing works. But the real explanation is a beautiful mix of physics, engineering, and even a little bit of art.
At the heart of flight is something called lift. Lift is the force that holds an airplane up, opposing the pull of gravity. Gravity is always trying to pull the airplane down, but lift pushes it up. So, where does lift come from? It comes from the wings. And here's the amazing part. Airplane wings are specially shaped, what engineers call an airfoil, to manipulate the air as the plane moves forward. You might be wondering, how does a shape create lift? Imagine slicing through the air with that wing. The top surface of the wing is curved, while the bottom is relatively flatter. When the airplane moves forward, air splits at the front edge of the wing and flows above and below it. Because of the wing's shape and angle, air moves faster over the top and slower underneath. And here's where some high school physics comes in. Faster moving air on top creates lower pressure, while slower moving air underneath creates higher pressure. The difference in pressure pushes the wing upward, and you have lift. But is it really just about pressure differences? That's one explanation, but it's not the whole story. Another way to think of it is Newton's third law of motion. For every action, there's an equal and opposite reaction. The wing pushes air downwards, and in reaction, the air pushes the wing upward. So, the next time someone argues whether it's Bernoulli's principle or Newton's laws that make planes fly, the answer is actually both. Engineers design wings to take advantage of both effects at the same time. Now, lift alone doesn't keep you flying. You also need thrust, the forward force that moves the airplane through the air. Without thrust, you wouldn't have enough airflow over the wings to generate lift. That's where engines come in. Jet engines on most modern airplanes, or propellers on smaller aircraft. These engines pull or push the airplane forward, allowing the wings to slice through the air and generate that much-needed lift. But wait, what about drag? Drag is the resistance you feel when you try to run with your jacket open on a windy day. Air pushes back, and airplanes feel that too. Engineers work hard to design airplanes with smooth shapes to minimize drag, because drag slows the plane down. Then there's wetter force of gravity pulling the aircraft toward Earth. So, flying is a balance. Lift must overcome weight, and thrust must overcome drag. If those forces are balanced properly, the airplane flies smoothly. Here's something cool. Pilots can control lift by adjusting something called the angle of attack, which is the angle at which the wing meets the oncoming air. Increase the angle slightly, and you get more lift up to a point. Push it too far, and the airflow separates from the wing's surface, and you get what's called a stall, where lift suddenly drops. That's why pilots carefully manage their controls during takeoff, climbing, cruising, and landing. Let's talk about takeoff for a moment. When you're in a plane and it's accelerating down the runway, those engines are producing massive thrust. As the speed builds, airflow over the wings increases, and lift starts to overcome weight. At just the right speed, called takeoff speed, the pilot pulls back slightly on the control column, increasing the angle of attack, and suddenly, you're airborne. It's a magical moment, but really, it's pure physics doing its job. And then there are flaps and slats, those panels you see extending from the wings during takeoff and landing. Why do they move? Because they temporarily change the shape of the wing, allowing it to produce more lift at slower speeds. That's why planes can take off from relatively short runways and land safely even when they're moving slower than cruising speed. But flying isn't just about going up. It's about staying stable in the air. Airplanes are designed with tails and control surfaces like elevators, rudders, and ailerons that allow pilots to control pitch, yaw, and roll. These surfaces ensure the airplane isn't just flying, but flying safely and predictably. Now, let's address a common misconception. Do engines hold airplanes up? No, engines provide thrust to move forward, but wings provide the lift. If you had powerful engines and no wings, you might move forward fast, but you wouldn't stay in the air. Wings are non-negotiable. Even gliders, which have no engines, can stay aloft by exploiting lift generated by their wings and air currents. Have you ever seen a bird glide effortlessly? Airplanes mimic that behavior. In fact, much of early aviation design was inspired by birds. The Wright brothers studied bird flight when designing their first aeroplane. Modern wings are far more sophisticated, but the principle is the same: shape, airflow, and balance. Here's another interesting point. Air itself is invisible, but it acts like a fluid. It flows, it changes pressure, it exerts forces. Engineers spend countless hours in wind tunnels testing how air moves around models of airplane designs to make sure they're efficient and safe. They use supercomputers to simulate airflow, ensuring every curve and angle of the aircraft contributes to stability and performance. What about turbulence? You've probably felt that on a flight and wondered if the plane is struggling to stay in the air. The truth is, turbulence doesn't threaten a plane's ability to fly. Modern aircraft are designed to handle far more stress than turbulence ever causes. It might feel uncomfortable, but aerodynamically, the plane is still flying perfectly, because lift is still greater than weight, and thrust is still greater than drag. So, what keeps airplanes in the sky? It's a combination of smart design, powerful engines, and the fundamental laws of physics. Lift from the wings counters gravity, thrust from the engines counters drag, and stability controls keep everything balanced. It's a delicate dance, but one that engineers and pilots have mastered to make air travel one of the safest forms of transportation in the world. And it's not just commercial jets. The same principles apply to helicopters, drones, and even futuristic electric aircraft. Each uses some variation of the same four forces: lift, weight, thrust, and drag to achieve flight. As technology advances, we're seeing new wing designs, lighter materials, and even AI-assisted flight controls, making airplanes more efficient and capable than ever before. So, next time you're on a flight and you hear the engines roar at takeoff, or you feel the gentle bump of turbulence at 30,000 feet, take a moment to appreciate the incredible science and engineering at work. Those wings, that thrust, and the invisible air around you are all working together, following the unchanging laws of physics to keep you safely in the sky. Thank you for joining me once again on the Circuit Forge Network as we explored what makes airplanes stay in the sky. If you enjoyed this breakdown and want more deep dives into how the world works, please like this video, subscribe to our channel, and share it with someone curious about flight. And don't forget, we want to hear from you. What technology or science topics are you curious about? Drop your suggestions in the comments, and we might feature them in our next episode. Until next time, keep learning, keep exploring, and keep flying high with us here at the Circuit Forge Network.